How did the best part turn out to be 19,000 parts? Elon is known for adopting the aphorism that the best part is no part at all. So how did thermal protection for Starship turn into 19,000 heat shield tiles that didn't quite protect the control surfaces on Starship's atmospheric reentry on the fourth test flight? The answer is interesting at a number of levels. By iterating toward a final design in a hardware system as big as Starship, decisions start to have a legacy that echoes through subsequent decisions. Why is Starship made of stainless steel? In part because the initial idea was not to have any kind of heat shield material attached to the stainless steel body of Starship. The initial idea was to depend in part on the inherent heat tolerance of stainless steel and to use water or a cryogenic coolant to keep Starship's stainless steel shell from melting. Tiny perforations in the stainless steel skin would allow the coolant to transpire and cool the outside of Starship's skin. The vision was Starship as a gleaming, sweaty shaft that could plunge through the heat of the outer atmosphere, penetrating it over and over without damage. It was too difficult. Probably too difficult to build because the idea was never tested. Nevertheless, Starship remains a stainless steel rocket. By now, stainless steel fabrication is far too embedded in the way Starship is designed and built to change that decision. Iteration works for software because few decisions about software are so irrevocable. Even major parts of a software system can be replaced. You'll see this in AI-enabled software. The AI engines that those software systems use are readily swappable. In rockets, the material you make the rocket out of is a decision that's difficult to change no matter what the results of subsequent iterations tell you. One of the reasons that the design of new cars, especially EVs, takes only about 2 years now is that almost all the engineering is done in the digital domain. This applies to test and validation of the design especially. Engineering a mass-market car used to require building hundreds of prototypes. Only by building and testing the designs for manufacturability, ergonomics, weight distribution, crashworthiness, etc., could you be sure that what the engineers specified would work together. Now almost all of that can be done in the digital domain. This approach is frequently referred to as a digital twin. And this once again illustrates the difference between engineering a vehicle and creating software. You don't build a digital twin for software. You don't need to. Software is malleable enough. A giant steel rocket? Not so much.